Questions about anything? Oh, there's a couple more things I wanted to say about L'Hopital's rule. So here's some classic L'Hopital's rule examples. And they are that, well, let's see, in words, the natural log of x grows slower than x to the 1 over n. So you know the square root thing is a parabola tipped on its side. It grows kind of slow. And you take the cube root, it grows even slower. And when you take the nth root, you look at it and graph it and you realize it grows incredibly slow. So it grows slower than x to the 1 over n for any n. And what that means is that the limit as x goes to infinity of the natural log of x over x to the 1 over n is 0. And if you think about an indeterminate form, log of x goes to infinity plus infinity as x goes to infinity, and the nth root goes to infinity as x goes to infinity. And so this is the indeterminate form infinity over infinity. And x is going to infinity. So that's different than any version of L'Hopital's rule I mentioned last time. And a similar fact that you learned in freshman calculus is that e to the x grows faster. So this one's a slower, this one's a faster than x to the n for any natural number n. And that's going to mean that, let's say if e to the x grows faster, then one way to express that would be limit as x goes to infinity of, let's see, I could put the e to the x on top. If I put the e to the x on top, then it would mean e to the x over x to the n is plus infinity. Or another way to say the same thing is that the limit as x goes to infinity of x to the n over e to the x grows much faster, that's going to be 0. Okay, and so the question is, how would I use the same ideas I used to get L'Hopital's rule to demonstrate this? And the key is the, so let's see, let's think of a theorem. What theorem do we need? Well, let's see, these functions, log x and x to the 1 over n and e to the x and x to the n, they're non-vanishing for big enough x. And their, let's see, and their derivatives are non-vanishing. So let's suppose we have, let's see, we're going to have an f of x over g of x, and we're going to have an f prime of x over g of x, g prime of x. We're going to want to use the extended mean value theorem. And let's see, if those quotients are going to make sense, then g and g prime need to be non-vanishing. Let's see, so what theorems do we need? Question mark. We see right away that we need g of x and g prime of x to be non-vanishing. G prime of x, non-vanishing. for x bigger than something. Let's see, what else do we need? We need f differentiable. Let's make it need f and g to be differentiable. For big X. Let's see, what else do we need? We want to deduce the limit about f of x and g of x. Let's see, do we need... we assume the limit as x goes to infinity of f prime of x over g prime of x exists. So that's going to be L, the limit. And then we're going to want that the limit as x goes to infinity of f of x over g of x without the primes equals L2. Okay? And the main tool for doing this is going to be the extended mean value theorem. So let's see, what is that? That would be f. I'm going to put here x1s and x2s instead of, let's see, what's the extended mean value thing? I'm going to make it x2 here minus f of x1 over g of x2 minus g of x1. And the extended mean value theorem said there's a c between those 2 points so that you get kind of a mean value theorem, but a fancier version of it. Okay? That's Cauchy mean value theorem in the book. I call it extended mean value theorem sometimes. Okay. Well, we certainly have those conditions in the case of the exponential function and the log function and the nth root function. So we have all those conditions, and so we would have this thing. And so what's the idea? Let's see, the picture here would be x1 is going to be less than x2, and c is going to be someplace in the middle. Okay, and I know that the f prime of c over g prime of c tends to L. So here's what I'm going to do. Here's the big idea. It's going to be very simple to do once you realize what the heck you're going to do. The big idea, pick a big x1 to make c big enough that f prime of c over g prime of c is close to L. As close as we want. This is kind of lazy proof, limit proof language. It's the way I would explain this to my freshman calculus class if I had to. But you know what that means. Let epsilon be bigger than 0. There is a x1, etc., etc. I don't want to say all those words. Okay, so I'm going to pick an x1 to make c big enough that this is close, namely with an epsilon, to L as we want. And now you think about, well, what else could I do? That would make the right-hand side getting close to L. I have to relate the left-hand side to the quotient I care about. My x1 is stuck now. So I can't move it around and make it go to infinity. So x1 is stuck. The aha moment is we can slide x2 out as far as we want. We can let x2 get gigantic. What did I say? X2, yeah. Okay, let's think about what that would do. Let's let X2 get gigantic. Well, let me think. I'm still thinking. Copy this thing. Okay, I'll rewrite it here. What's the plan? What? I forgot to copy it. Sorry, that was stupid. Guess I could have rewritten it in that time. Copy. Paste. Okay, and now I have, what should I do? Any ideas about what I should do to get, I want f of x over g of x. And x2 is going to be big, so I want f of x2 over g of x2. How should I get it? Any suggestions? That's what I know, and the thing on the right is getting close to L. And I want the thing on the left to look like f of x2 over g of x2. Add it? I want to get a ratio. I want to get a... Oh, I see what you're saying. That might do something. But I wish I had f over g, and I have it kind of jumbled up in a mess here. So the thing that I thought of doing is multiply the top and the bottom by 1 over g of x2. Okay, if I multiply the top by 1 over g of x2, I have to do the same thing to the bottom. And then let's look at, well, remember g of x2, g of x is going to infinity. So that's a big number. So I can assume x is bigger than m to make that thing non-vanishing, and I know that g of x goes to infinity, and so that's a big number that I'm dividing by. And on the top, I get f of x2 over g of x2 minus f of x1, which is just a number, divided by a gigantic number. That's interesting. And on the bottom, I get 1 minus g of x1, which is just a number, stuck number, divided by a number that's getting gigantic. How cool is that? All right. So let me see. I can solve for the quotient I want, and that's approximately L. And so if I solve for L, I see that f of x2 over g of x2 would be equal to f of x1 over g of x2 plus L times 1 minus g of x1 over g of x2. And now when I realize, aha, I can let x2 go off to infinity. And when I do that, so the aha here is let x2 go off to infinity. I wouldn't have changed how close that thing is to L. I let x2 go to infinity, and note that g of x2 goes to infinity. As x2 goes to infinity. Okay, and so this thing is going to convert, this thing is going to go to number divided by something gigantic. That tends to 0. L just sits there. 1 just sits there. And then this one, g of x1 is just a number. x1 is stuck. So that's just a number that sits there. And I'm dividing by g of x2, which goes to infinity. So that tends to a big fat 0. And so I see that the left-hand side tends to L times 1. See, what we see is that f of x2 over g of x2 tends to L as x2 goes to infinity. Okay. And so, of course, if I was going to use the full-blown language of math proofs, I would have said let epsilon be bigger than 0, and I'd be doing inequalities to see that, aha, I made this within epsilon of L, et cetera, et cetera. But if you understand the words that I've said, then you could write down that argument if somebody locked you in a room and made you do it. Questions about that? That's kind of cool to see that those theorems that they just fed you, perhaps, in freshman calculus are not hard to deduce. And they make perfect sense once you see the extended mean value theorem. I figured now that we know these facts, we might as well do those famous freshman calculations. Let's do, let's see. The limit, I'll do x to the n over e to the x as x goes to infinity is equal to the limit n times x to the n minus 1, and when I differentiate the top, let's see, I don't know this yet. I'm just playing games here. Derivative of e to the x is itself. And I can keep doing this. The next one would be limit as x goes to infinity. I still don't know anything yet. I'm just doing this for kicks. Times n minus 1, x to the n minus 2. Derivative of the bottom is e to the x. And I would do it. And I eventually would do it until I got n factorial, a constant, over e to the x. And you know that e to the x goes to infinity because e is bigger than 2. And so e to the n would be, e to something big would be like 2 to the n, which we know from earlier goes to 0, goes to infinity. So this one is equal to 0. And this is the starting point. Start here. Okay, if we know that thing, limit exists, then we use L'Hopital's rule, the version I just told you, to see that the previous one does. And now that I know that that one does, the previous one does, until I get all the way back to the first one. So it's just sort of using L'Hopital's rule, starting with sneaky business of doing it n times before you even begin. So that's a fun thing from freshman calculus. And similarly, the calculation for the log business, it's more straightforward. Let's see, which way was it going to show? Limit of the log x over x to the n, of x to the 1 over n. If I put x to the n there, well, let's see, that would go to 0 even faster. And so L'Hopital's, I guess I should say, these are question marks. Until I start, when I start here, then I can undo the question marks going backwards. And so the answer is going to be yes here, and yes here, going backwards. Okay, let's see, this one, the derivative of log x is 1 over x. I think I showed you that at some point. Inverse function theorem. Derivative of x to the 1 over n is 1 over n. x to the 1 minus 1 over n. And that's already easy to see is 0. Is it? X to the 1. Yeah, so that this thing right here, we'd get an n on the top. What do we get? Yes, definitely. Thank you. 1 over n minus 1. And that would be n over x to the 1 over n. And as x goes to infinity, that's 0. So I don't have to do the doing it n times and going backwards thing. So check. Questions about that one? Okay. I'll let you read the rest of that section carefully. All of the famous L'Hopital's things, there's lots of cases when you get down to it, hold. And it's because you can play this game with the extended mean value theorem. Well, that brings me to today's topic, which is Taylor's theorem. So the mean value theorem is one way. The mean value theorem shows f of x can be approximated very closely by f of x naught plus f prime of x naught times x minus x naught, for x close to x naught. Close to x naught. And so the words that we like to use is this is the best linear approximation to f of x near x naught. And you can even get, why not do, let me show you something. Excuse me. Let's see. The mean value theorem shows that. So let's see, I would have f of x minus f of x naught over x minus x naught. That's equal to an f prime of c by the mean value theorem. So let's see if I solve this gives me an equality. F of x equals f of x naught plus f prime of c. Of course, c depends on x, so that equality isn't true for all x. C depends on x. Important to keep that in mind. And so let's see now, if I subtract that linear, if I take f of x now, f of x minus, let's see, that linear approximation was f of x naught plus f prime of x naught times x minus x naught. So how close is that? When I subtract that junk, when I stick this junk, I'm going to stick this junk in for f of x. And then a lot of stuff cancels, and I'm left with f prime of c minus f prime of x naught times x minus x naught. Okay? If the derivative is continuous, then that thing is small. In fact, let's think about it. This is just a way of playing around. If f prime is differentiable, I can do the mean value theorem again. What would I get? Let's see, when I get the linear, here it is. It's f prime of c minus f prime of x naught over x minus x naught. That would be an f double prime of something. I need another letter. A, B, C, D. D would be between C, x naught and C. And I guess I should move it down a bit. And so how neat is that? That's, I can multiply through by that. This is what I'm estimating over here. Oops. Estimating this. And if I put the x minus on x naught on the other side, I would get that stuff in the square brackets, f of x minus the best linear approximation equals f double prime of d times x minus x naught squared when I stick it in there. That squared is exciting. And so if that second derivative is bounded, I see that when I subtract off the best linear approximation, I get something that vanishes to order 2. So here's something cool. F of x minus the best linear thing let's see, if I was going to estimate this thing, that's less than or equal to the maximum of the second derivative on some interval times x minus x naught squared. Okay? That's kind of a typical use of the mean value theorem to estimate errors. So if somebody asks you, well, that's a good linear approximation, how good is it when I'm a little distance away? This allows you to estimate the error. And it's useful if you're doing numerical analysis. Also, when you're demonstrating certain facts about differential equations. Anyway, that's the point of this next, that best linear approximation has the same value as f and the same first derivative of s. So f of x naught plus f prime of x naught times x minus x naught has the same value as f at z naught and the same derivative. The derivative of that function is f prime of x naught. And then you ask yourself, well, how could I add a best second order approximation? Make the derivatives, excuse me, the derivative the same, the first derivative the same, and the second derivative. Okay, the value has to be this. This would still have to be the next term. But to make the second derivatives match, you can figure out by writing it out and setting it equal to what you want it to be. the next term would have to be this. That has the same second derivative at x naught. And I don't mess up any of the previous stuff. That's the cool thing. So I don't mess up the value at f, x naught. I don't mess up the first derivative at x naught, because that derivative of the last term vanishes to order 2 there. And when you calculate the second derivative of that and stick in x equals x naught, you get f double prime of x naught. So you get, this agrees to order 2, etc. And Taylor realized I could do this indefinitely. This agrees with f to order 2 at x naught. And the etc. is Taylor's theorem. Okay, so we want to get Taylor's theorem. It is that f of x equals f of x naught plus first order term plus 1 over 2 factorial f double prime of x naught over x minus x naught squared plus dot dot dot. The general nth term is nth derivative of f at x naught divided by n factorial times x minus x naught to the n. And then there's a remainder term. A remainder term after adding the nth one there. And the deal is that remainder term goes to 0 very rapidly as x tends to x naught. And also I'm going to get you a, so let's see, what do I need? I would call this a super duper mean value theorem. This is all this is. Let's see, what are we going to need to make this work? We need the derivative, we need f to be differentiable enough to make this formula make sense. So we need f, f prime, f double prime, and f nth derivative prime to exist and be continuous. So they all exist and are continuous. Okay, we need that. We need the next derivative to exist. Also need next derivative to exist, at least. It doesn't have to be continuous. That's kind of like the mean value theorem. The derivative has to exist, but it doesn't have to be continuous in the mean value theorem. Well, this was going to be the next derivative has to exist. Okay, and then the super duper mean value theorem, it says that that remainder then there is a C between x and x naught such that that remainder can be expressed in terms of that, kind of like what I did in my playing around with linear approximations, such that the remainder term there is 1 over n plus 1 factorial times the, let me put the derivative on top here, the nth plus first derivative at c times x minus x naught to the n plus 1. So that means that that Taylor polynomial agrees with f so closely that the error there vanishes to order n plus 1. So the closer you get to x naught, the incredibly much smaller that error is, especially if n is a big number. Okay. So I mean, this might sound exciting if you're trying to approximate locally by a polynomial, because I just showed you a polynomial that's nice and close there. The mind-blowing thing is that sometimes this estimate, this error estimate, can show that the Taylor series converges to the function. So a mind-blowing fact can easily use this error estimate, use this to show that the famous power series for the things like x is actually equal to 1 plus x squared over 2 factorial plus blah, 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 for all x. And sine of x, for example, equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. I'll write one more. Plus dot, dot, dot for all x. That's a mind-blowing thing, and I don't think Taylor expected to get it. Well, maybe, I don't know. But he's the one who figured out a way to demonstrate that this actually happens. I think Euler probably realized that too, but he write down this formula. Let's see, how do you do it? It's just pure fun. Let's show the example. Oh, by the way, the proof of this Taylor's theorem is just it is just a fancy mean value theorem. And so you think of a way to reduce it to Rolle's theorem in an incredibly clever way. So Taylor, we get C from a very clever, we get C from a very clever application of Rolle's theorem applied to a very clever choice of a function. It's a function that vanishes at but it's only one little paragraph, and it's on page 189. It's not hard. You just say, well, where the heck did they get that? Short and sweet. So it's short and sweet, but you'd have to think about how in the heck did they come up with that function? But perhaps mysterious. It's worth reading, and it's just a matter of verifying, oh, sure enough, that Rolle's theorem function vanishes at the left and vanishes at the right, and sure enough, at the max it has a derivative that's 0, and that's where you get the remainder term in the Taylor's formula. Okay, let me show you that power series for sine converges to sine. So let's see. Let's take an example here. F of x equals sine of x. Okay. Then f prime of x is cosine x. F double prime of x is minus sine of x. And you just, after that, you just alternate by, let's see, f triple prime would be minus cosine of x. And finally, it's going to repeat here. F fourth derivative of x is sine and after this, you just start repeat. Okay, and sines and cosines are all bounded by 1. Okay, it's an important thing. Sine, cosine are all bounded by 1. And so when I do the Taylor's theorem with remainder, no matter what x I'm doing, I would get that the remainder term, r sub n of x, would be an n plus first derivative at c divided by n plus 1 factorial times x minus x naught to the n plus 1. And because all those derivatives are bounded by 1, this is going to be less than or equal to x minus x naught to the n plus 1 divided by n plus 1 factorial. And that's one of those things, that goes to 0 as n goes to infinity, no matter what the x is. Because n plus 1 factorial goes to infinity much faster than a power of that thing on the top. We want to think about that? That might be fun. The deal is, we'll think about the case where x minus x naught is less than or equal to 1. And that would go to 0 incredibly fast. And you could see, oh my gosh, this thing is sailing in really fast. But even if x minus x naught is 100, then you get 100 to the n plus 1 on top. That's a good way to think about it. Let's say x minus x naught is 100. I get 100 to the n plus 1. But if n was bigger than 100, then I'd get a finite number of terms that are kind of annoying, but all the rest would be less than 1. And I could make that n get really big and get something less than 1 to a gigantic power. So it's not hard to show that that goes to 0 as n goes to infinity. For any x, for any fixed x. And x naught. And one of my favorite graphs to demonstrate in freshman calculus is how beautiful that convergence is. So let's say the sine function wiggles like that. The first best linear approximation is the first degree Taylor polynomial is tangent at the origin. Then the next one, the second one, this would be the second order one, looks like a parabola. It would hang on, and then it would go sailing off like a parabola going like that. Then the next one, the third order one, let's see, I think it goes underneath. It hangs on longer. Where does it go? I should have graphed this using maple. It hangs on, but then it goes up. And the more ends you ask, it hangs on for more humps before it peels off and goes away. I think the orange one goes above. Orange one goes above the blue, hangs on, and then takes off. The next one would go underneath. Hang on. Anyway, when n gets really big, it hangs on longer and longer and closer. So it'll be really close in the early part, and before it peels off. When it starts peeling off, it loses it bad. Anyway, that's a mind-blowing thing, and I guess in freshman calculus you might be led to believe that functions are equal to their power series. But if that famous thing I showed you, here's a famous function. Let's see. Let's have f of x be equal to e to the minus 1 over x squared sine 1 over x for x unequal to 0, and 0 for x equal to 0. That's a famous function. F and all its derivatives, it's actually C infinity smooth. It's infinitely differentiable. Is C infinity smooth, even at the origin. F and all its derivatives vanish. And so its Taylor series is just the zero function. And of course, it's not the zero function. So the bad news is for people who love power series is that F is not equal to its power series. Or I'll call it Taylor series. So that's a disappointing moment in history when people realized there's infinitely differentiable functions that are not equal to their Taylor series. And so the subject of which ones are turned into my subject called complex analysis. Complex analysis studies, you let the x become a complex number, and then understanding the convergence of power series is makes a whole lot more sense. So for example, in the complex plane, the radius of convergence is really a radius of a circle. And so it's a circle in the complex plane where the power series converges. And that's the subject of Math 425. The blast. So that's an advertisement for 425. Any questions about today's stuff? Yeah, so exciting announcement. We'll start chapter 7, which is about Riemann integration, the Riemann integral. So we've finished off differentiation, and now it's time to start thinking about integration. There's a lot of famous formulas for that remainder term in Taylor's formula, and many of them involve integrals. So, and depending on what you're studying, this mean value version or an integral version would be the most useful. But it's kind of mind-blowing that you can get such an estimate without doing integration. Okay, well that's enough for today.